My name is Ben Coverston. I work at DataStax. This talk is building a distributed data platform. I decided this is probably a pretty good talk for me to give since I'm sort of in charge of building a big data platform at the place that I work. I work for, again, DataStax. Let's see if I can not say that in the next 5 minutes or so. I've worked there since November of 2010, back when we were called Riptano. And when I was originally brought on to DataStax, we've got sort of a unique way of hiring people. So very early on, we found that the people who were most appropriate for working on Apache Cassandra were the people who were already working on Apache Cassandra. And so a lot of times we hired people who were committers. And the nice thing about hiring people who are committers or contributors to Apache Cassandra is that you get to see their code before you hire them. The other thing is you get to know them, and because they enjoy contributing to open source or enjoy contributing to Apache Cassandra, they'll probably like the work they do once they get there, right? So does anyone here belong to the Utah Python user group or regularly attend the Utah Python user group? So do you know Jonathan Ellis? No? Okay. Okay, all right. So he sort of bootstrapped the Utah Python user group here in the state. And then he went on to work for a couple places, ended up at Rackspace, started working on a really early version of Cassandra back when Facebook just sort of open sourced it. And the way Facebook open sourced Cassandra is they were kind of like, here world, here's this code. And basically didn't do anything with it after that point. So he picked it up, started working on it. And I knew Jonathan from working in a couple places with him here around the valley. And he kept pinging me, and he was like, hey, why don't you come and work with me at my little startup? And I was like, well, how many people are you guys right now? Because I had a nice cushy job at the time at, a Fortune 500 company. And I didn't have to, I wasn't responsible for a whole lot of things, but I got to do what I wanted to do. So I wasn't really interested in moving along. And he was like, well, we're 6 people. And I was like, that's too small, too risky. I don't think my wife will go for it, right? Because, of course, that's the thing that really matters when you're looking for a new job. And so, later on, he pings me again. He's like, hey, do you want to work on this Cassandra ticket? So he gave me this thing to work on. I looked at it. I was like, I don't know if I have time. So I spent, probably a month looking at it and then working on it. I ended up contributing some code, not just to the Apache Cassandra project, but also to Thrift. And then at the end of it, in his style, he was like, well, you did a pretty good job at this. Why don't you come work for me? And I was like, well, I kind of enjoyed it. He's like, well, if you enjoyed the ticket and you enjoyed this, you'll enjoy working at DataStax. So so I talked to him. I talked to the co-founder. And then I flew out to Austin for my first day on the job. And the co-founder sat me down and he said, all right, I want you to work on Apache Cassandra, but I've got more pressing needs. The company's 15 people at the time. And I was employee number 15, and he was like, we've got all these hackers. We don't need people writing code. I need you to work on some other stuff. And he was like, I want you to be in charge of professional services, training, support, and oh, by the way, I can't handle sales right now. I was like, I'm not going to do this. What are you thinking? I'm a hacker. I don't know how to deal with this. He's like, it's just for 3 months. I was like, well, okay, I can do anything for 3 months. I'll do it for the company, right? I affectionately refer to this period of time as the longest 3 months of my life. Because it ended up being more like 2 years, right? And so finally, at the end of this 2-year period where I was doing mostly training for a lot of people, I'd go around and teach people about Apache Cassandra. I finally got back to coding. And so I've been in this role for about 1.5 years where I've been sort of shepherding a product called DSC, which is Apache Cassandra plus search extensions and analytics extensions, right? So a lot of the content of this talk talks about some of the things that you might consider if you're building or you're planning to use a distributed data platform. Now, just by show of hands, how many people in here would consider themselves a DBA or a DevOps person that does enough DBA stuff to be dangerous, right? Just raise your hands, right? How many people here have taken a relational database and had to shard it because it got too big? One person? All right. So I'll be talking to you a lot during this session, right? So a lot of times this is sort of what happens is, people build their systems on a relational database because that's what they know or that's what's familiar, right? There's the old adage, back in the old days, people used to say nobody got fired for using IBM. And today, a lot of people will use that same thing and they'll say nobody got fired for using Oracle. And if you go down the rung, you may get down to MySQL or MariaDB. And these are technologies that are familiar to all of us. Most of the people in this room, I imagine, can write, a non-trivial SQL statement to grab data out of a relational database, right? And this is kind of where we are. However, in a lot of cases, we get to the point where a relational database isn't a good fit, or we have to shard a relational database because our data gets too big. In which case, we end up building a system ourselves. Maybe a system to do OLTP transactions because that's what our main use case is, or maybe a system that does OLAP, right? The reality is, even though we have two separate terms for this, traditionally, at least in the relational world, OLAP and OLTP systems have often been the same thing and only separated if they needed to be, right? So you push your OLTP system as far as you can, and as long as you can still get your low latency response from your OLTP system, you can still do your OLAP queries there, or you can do them at night when your users aren't on your system and you can afford to use those resources, right? So traditionally, in small cases, they've been the same database. But in a lot of cases, people will create separate systems or systems optimized for each OLTP and OLAP, right? And sorry, that's a problem with my slides here. So we optimize them for different use cases, and often we have two separate systems. And having two separate systems to do these two separate things often means this, right? Who's ever been involved with a project to do ETL? Yeah. Was it fun? Yeah, most boring work you'll ever do, probably, right? Take data that looks like this over here and turn it into something that looks like that over there, right? So ETL is not fun, right? There are a lot of bad things about ETL, right? ETL means you have to move data from one place to another. Moving it from one place to another means you either have to span a LUN, or more often, and more likely, you'll have to span a network segment, right? And how long does it take to throw a terabyte of data over your network? A long time, right? Best case scenario, you're talking about hours. Worst case scenario, you could be talking about days, right? And this is one of the reasons why when we talk about databases and we talk about OLTP databases, this is one of the primary reasons why you'll look at systems like Cassandra, or you'll look at systems like Couch, or systems like even MongoDB, or you'll look at systems, just pick your distributed database. And if it's an OLTP style database, they'll tell you, you know what? You could stick 10 terabytes of data on this single machine, but you probably shouldn't. And why shouldn't you? Well, there are working set concerns, of course. You can only fit so much of your data in memory, and you don't want to have to go to disk for everything, because if you have to go to disk for everything, then you'll start queuing. And if you start queuing, then everything's going to be slow. And you can buy SSDs to help you out with that, but even if you buy SSDs, if that machine fails, you have to recover the data from somewhere else. And somewhere else means that it's on tape, or it's on another machine on the network, or somewhere else. So you want your recovery times to be relatively low. And I'll talk about this term a little bit later, and that is MTTR, mean time to recovery. And you want that to be relatively small in a distributed system. So ETL is bad. And a lot of times, we want to process the data where it is, right? ETL takes time. It's expensive. We want to avoid it. We as programmers don't really want to do it, right? So there's tooling out there that helps us out with it. And if you can avoid ETL for most of your data, at least for your operational data, the data that you use on a regular basis, hopefully you can do your OLAP and your OLTP in the same system, right? So let's look at some of the use cases. So in general, when we talk about distributed systems and OLAP and OLTP, in the OLTP world, we're talking about databases like Cassandra. We're talking about databases like REACT. We're talking about databases like Mongo or Couch or something like that, right? On the OLAP side, generally we're talking about a batch-oriented system, right? And in the big data space, there's kind of one big player, and that's Hadoop, of course. We want to talk about the elephant in the room, right? And so a lot of this stuff here is oriented toward sort of how Hadoop might work, or specifically the HDFS, the Hadoop distributed file system, right? So in an OLTP system, a lot of times when we query it, we want our latencies to be relatively low. We're talking about latencies on the order of milliseconds. If your latencies aren't on the order of milliseconds, it's not an OLTP system, or it's a really slow OLTP system. A lot of times we want to optimize for cache in those cases. OLAP, generally your answers are going to come back in minutes or longer, right? MapReduce jobs are, they can be long running and they can run for hours to days if in some cases. Now there are some optimizations and some new systems that are available out there. We'll talk about those in a little while. But if you've looked at things like Spark, Tez, Impala, there are MapReduce style systems or analytical systems that work on big data that can, in some cases, return your results in seconds, where before they might have taken minutes or hours before. For OLTP system, generally you've got some type of indexing so that you can find your data relatively quickly. Indexes generally on the surface in a distributed database, however, are relatively limited, and usually there's some primary key indexing and then some limited secondary indexing. That's pretty standard in distributed databases today. On the OLAP side, we often ignore indexes entirely, and we just read all of the data sequentially, right? And in many cases, the data that's stored in, especially things like HDFS, is unstructured, right? So you have to go through it, and you have to parse the data out every time, split it up, and do whatever processing that you want to do with it. On the OLTP side, complex analytics or in-depth querying isn't usually something that you can do. Again, you can query on the primary index. You can maybe do some stuff with secondary indexes, but there's not a lot more that you can do. On the OLAP side, of course, you can do deeper and more rich querying. If you want to scan a record or a set of records out of a system, many distributed databases, particularly Cassandra, is pretty good at doing short scans because of the way it structures the data out on disk. So if you want, for example, if you're doing time series data, you can grab the key, and then from the key, you could say grab a range of data inside of the row that's associated with that key. And when I talk about keys in Cassandra, I'm talking about, in Cassandra we use a special term called a partition. And a partition basically means a key that points to data, and all of that data is physically co-located, right? So we talk about partitions in a little bit different way than you'll see. A partition isn't necessarily a physical machine in Cassandra, for example. A full scan, not something you usually do in Cassandra. Even if you're doing a full scan of a single machine, you'll probably have to seek around a little bit to get through all the partitions. So generally, we want to avoid seeking in an OLTP database where we don't need to. And then relationships in a distributed database, generally you abandon the concept of trying to physically represent your relationships inside the database. So there's no such thing as a join. In most distributed databases, and almost all distributed databases, they kill your performance in general because of the amount of seeking that you have to do. And then in the OLAP side, again, they don't physically represent your relationships, but because they scan through all of the data, those relationships can be materialized inside of the query itself. And then for sequential writes, relatively easy to do on the OLAP side. And in some cases, depending on the database, you can do sequential writes there. Updates in OLTP, obviously, you can do them in a random sequence. Some databases are actually structured to do sequential updates as well. And then on OLAP, they're really optimized for batch updates in that way. So there are multiple types of OLTP stores in the distributed world out there. Who here is familiar or has heard of the CAP theorem before? Okay, so basically there's this guy, Dr. Brewer. He wrote this paper, and it's relatively famous in this distributed programming or the distributed database world, or even in distributed computing in general. He said there are three elements to any distributed system. You can have consistency, you can have availability, and you can tolerate partitions in your database. And when I say you can tolerate partitions, imagine you have a network of machines and you start losing network partitions between your machines. So the machines fail to talk to each other over time when you lose these partitions. So when you're building a distributed system, you have to assume that you will get partitions, right? Network segments will fail, machines will fail, things won't be able to talk to each other. So we assume that you have to take P. So that leaves two things that you can tweak in a distributed system. You can tweak availability, or you can tweak consistency, right? So the more you get of one, the less you get of the other. So the more consistent your system is, the less available it is, right? And the less consistent it is, or the less consistency that you guarantee, the more guaranteed availability you can get, right? So you can choose one. It's not like you can choose all of one or all of the other, right? You can choose an amount of one, and that will give you less of the other, right? So if you try to choose infinity of one or infinity of the other, you get nothing of the other, right? So you have to choose between these things. So you get a mix, and some systems emphasize consistency, some systems emphasize availability. And none of them are 100% one way or the other. They all present to you a choice, or they all present to you a certain level of consistency or a certain level of availability. And I'll talk about some of the systems that do this. I'll give you a couple of examples. And if you don't think you're using a distributed database right now, one thing to keep in mind is that almost everybody runs a distributed database today. Because either you have one and you have a mirrored copy, right? Or you have one and you have a tape backup, right? And there's something that happens between, or an offline backup. And there are things that happen between when your operational store retrieves their data and you create your backup that you do to try to mitigate the amount of loss that you have, right? So whether you like it or not, you have to deal with the CAP theorem, right? Even if you have a single system. Because if you want it to recover, if you want to deal with recovery at all, right? So the obvious choice is to choose consistency, right? That's what most people choose. That's sort of the model that relational databases are built around, right? You have a single master. That master receives writes. Those writes are then propagated to a slave, right? This is a typical CP system, right? If the master fails, then the slave takes over, right? And a lot of times people want more than that, right? They don't want just a single slave that they replicate to. They want multiple slaves that they replicate to. And then having multiple slaves means that you're writing to multiple slaves, but what if you want to read from those slaves? Well, your reads may not be 100% consistent if you want to read from those slaves, right? So a lot of times people will do some operations on those slaves that don't require 100% consistency or all the updates that have been received from the master, right? But then when you have two slaves, you've got a more complicated problem, right? So if your master fails, who's the new master of the two slaves that you're writing to, right? You'd need a third service, and a lot of people call this an arbitrator, to decide who the new master is of those two, right? Any questions up to this point? No? So there are a lot of hard problems that you have to solve in a master-slave system because, or in a CP system, because you expect there to always be a single source of the truth, right? Somebody in the database, a whole bunch of people may have this data, or a whole bunch of partitions may have this data, but there's only one that you can go to get the truth, or the single source of truth, right? And failover becomes more complicated in a CP system. And what happens to the writes that, how do I recover or how do I know which of my slaves got all of the writes that hit my master before my master failed? Or, is there some time in which I my system was not available after the master failed before the slave was elected, right? So there are all these issues with consistency or requiring consistency that make availability a harder problem when that's your focus, right? The other thing is that sharding is harder. So a lot of times you don't just have a single master and 2 slaves, but you'll break up your data onto multiple shards. So if you look at the way that eBay was architected, or if you look at how eBay looked back in like 2005, eBay uses a lot of relational database technology, and they shard their system based on a relational database technology. So if you look at their catalog, or if you looked at their catalog back in the early 2000s, the early part of the decade of the 2000s, they basically had a bunch of relational databases. And they took their catalog and they said, we'll stick everything that starts with A on this database, everything that starts with B on this database, everything that starts with C on this database. So they basically sharded out their catalog. And they said, we'll stick all of our data on all these different catalogs, right? So each one of those databases or each one of those masters were the source of truth for that partition of the catalog. So this one has all the truth for A, all the truth for things that start with B, all the truth for things that start with C. And so they didn't just have a single master and slave, but they had partitions of masters and slaves throughout their system, right? And this is where if you decide not to use a database that automatically partitions your data, this is where you end up if you don't plan on how you're going to scale your system, right? So they created the system, and each master had a slave, actually multiple slaves, and they had all kinds of systems to coordinate it. So they basically built their own distributed database out of all of these relational stores, right? And then if they decided at some point they wanted to take that the S's got too big, right? The catalog for the S's got too big. They had an external coordinator that said, hey, if you're looking for something in this catalog, then look in this location. And when we shard it, you'll have to look somewhere else, right? So they had an external coordinator that did some type of locking that said, okay, now that this has gotten too big, I need to shard it further, right? And so you require a third system to be able to migrate your shards and change your sharding algorithm, right? So things get pretty complicated pretty quickly in a consistency-oriented system. They're often brittle as well in failure scenarios. And high availability in these cases usually doesn't mean the system can never be down. High availability in these cases usually means that we're going to recover quickly or as fast as we can, right? Which is kind of weird for me because I never think of high availability as my system was down and is now recovering. High availability always means to me the system was never down. So what do systems like this end up looking like in the real world? This is an example of what, say, a Mongo database might look like, where you've got these Mongo data servers up here, right? These are your shards, right? And notice how they're siloed. These are different partitions of the same database. And then you've got some configuration servers that manage configuration on all of these. And then these Mongo S servers, which manage the data or the shards, or when the client needs to get a particular key, he talks to that guy, and that guy forwards him on to another one of these shards so that he can actually read his data, right? Pretty typical. Similar pattern here. This is HBase. And HBase, when an HBase client comes in to talk to or find a piece of data, he has to go and talk to a region server. And the region server basically deals with the sharding and the distribution of the data within the data nodes themselves. So that's kind of where consistency-based systems go, right? If you choose availability, then you get a whole different type of, or a whole different set of trade-offs. An availability-based system usually looks like a peer-to-peer system, or all the nodes look the same, right? There are no shard servers, there are no configuration servers, there are no masters, there are no slaves. You just have data nodes, right? In most peer-to-peer systems, at least the peer-to-peer systems that I'm familiar with. the way that the data is distributed is usually determined by some consistent hashing algorithm. So instead of using a server to tell you where your key is, another system to tell you where your key is, you just use math, right? If I have a key of Bob, I'll run Bob through a hashing algorithm. Out the other side, I'll get some MD5 hash, right? And I'll take that MD5 hash, and because my tokens own ranges of the range of the MD5 range, right? I can just be redirected to the right node without having to do anything special, right? So I can just go to any node in the system, ask for a key, and that node will redirect me to somewhere else in the system that has the data, and then broker that back to me, right? In these systems, failure is also not a special case, right? So if I have a peer-to-peer system and one of my nodes fails, all the rest of the nodes in the system just continue working the way that they did. And assuming I have multiple replicas of my data in the system, if a node fails or if a partition fails in the system, then I'm redirected to a partition that's actually working, right? The trade-off is the one that failed may have had the most recent key for the data that I'm looking for, right? And so I may introduce some entropy in the data in the system. I may have entropy introduced in the system, but because of failure, right? And I may have to have some other system or some other things that happen in my database so that I can recover from failure, right? Which is why I say anti-entropy can be difficult, right? It's probably one of the more complicated parts of any availability-oriented system is that if I update the data in one place, right? So a lot of times particularly in Cassandra, you can have your data distributed across data centers, and your data centers can be on different continents, right? And so it's probable that during the course of the year that something will happen so that your data center in the United States can't talk to your data center in Ireland, right? And if he can't talk to your data center in Ireland for like an hour, you could get updates in Ireland and you could get updates in the United States simultaneously for the same keys, right? So you could overwrite data in one place or the other place, right? And then at some point, these data points have to converge. And for Cassandra, they use timestamps. For other systems, they might use vector clocks and require the clients to actually cause the data to converge in the way that someone else might define. But this is something that you'll find is different from the way an availability-oriented system works, right? Compensating for that entropy can be expensive. So when you run Cassandra or pretty much any other AP-based system out there, you'll probably have to run something called repair on occasion, right? And repair doesn't do what you think it might do. Basically, repair is a distributed rsync job. It says read all the data in this system, right, and create a hash tree, and then read all the data in the other system and create a hash tree, and then compare those hash trees together, exchange segments of data, and then merge them together so that they're all consistent for the point in time in which you ran the repair job. Not necessarily now, but now you're consistent in a point in time in the past, and all the while you've had more updates coming into the system, right? So there's no such thing as like an offline repair. Or more importantly, is that this is not like, this anti-entropy repair is not like, what do we call it in the relational world? When you're syncing two databases together, synchronous replication. It's not like that, right? Where if two things get out of sync, one will basically stop accepting reads in some cases. Cassandra will always accept reads. It will always accept writes. And so this is something you have to deal with, something different, right? So the other thing here is that your DBA will never know how far behind you might be in one data center or another data center. Because in order for us to know how consistent we are with the other data center, we have to start this repair job, which means we have to read all of our data and create this tree. So there's no way for you to tell how in sync you are. So a lot of trade-offs here, saying that we're going to be always available and eventually consistent means that we're making a set of decisions that may be unfamiliar to us, right? Now, HBase is widely considered to be a CP system, right? Consistency and partition tolerant, right? And this is somebody who works at Cloudera right here talking about at HBaseCon. And they're talking about eventually consistent systems, right? And jokingly they say eventually consistent stores are 100% consistent 99% of the time. And that's mostly true, right? I mean, but you have to add a couple more nines onto the 99%, right? It's more like 99 point. In most cases, it's more like 99.9999. I mean, it's rare to actually see inconsistency in an AP system because we do so much work on the anti-entropy side. If you miss a write, we write a hint. When you write into the database, we always try to write to all replicas. And if we miss one, we'll try again soon after, right? And then, you know, if something goes down and for some reason a hint doesn't get delivered, there's always repair that gets run. But still, this is true, right? It's mostly consistent, right? It's a very rare case that you'll actually see inconsistency. But even in CP systems, they see the need for AP features, right? So this is actually a feature that they've proposed in HBase that would add eventual consistency into HBase. So there's a lot of, and in Cassandra, by contrast, right, we actually allow people to choose the level of consistency they want on a per operation basis, right? So I think it's more common in distributed databases that people actually have the ability to sort of tune their consistency to their needs. And that's important because not everybody has the same use case, right? So I showed those diagrams of CP systems and how they often look. AP systems generally fall into this category where they have multiple nodes, right, that all sort of have the same role, own some piece of data, and then clients come in and talk to those nodes, and then those requests get brokered into the cluster. So this is one example. This is another example of what it might look like. In this case, we've got a multi-data center type scenario, right? So partition tolerance, of course, is the distributed part of your platform. And it's the one that allows for horizontal scalability. The problem with partitions, however, is that ad hoc queries become hard or impossible to do, right? And so, sorry, that doesn't belong here. So ad hoc queries are hard. Joins on partition tables are nearly impossible, right? So basically what you could say is, you know, if you had the same data or the same table distributed across multiple regions, right? Trying to join on some key inside of that table, even though the data is homogeneous across or congruent across all of the partitions, actually executing a join means that for each key, you have to take a key on a different partition and compare it to a key on another partition. Even on the same machine, joins are kind of the scalability bottleneck for relational databases. And the primary motivation for denormalizing most data in OLTP stores, even in relational stores, right? So even in a relational database, when you start to run up against performance bottlenecks, the first thing you usually run into is the join is slow, right? Well, why is the join slow? It's because for every single one of those keys, I have to consult an index, right? And if I exhaust and once I consult the index, then I have to go on to disk and I have to read the data off disk. And if I don't have enough memory on my machine to put all of my data in memory, or if my page cache gets exhausted, I start swapping. And if I start swapping, I'm lost, right? I'm not going to be able to do it. It only gets worse when you have to do it across multiple partitions and you have to span the network boundaries, right? So we just don't do that, right? So simple distributed queries are possible, however, in a distributed system. So in DSC in particular, we said, hey, Cassandra's great. You can go and you can grab a key and you can read the data from that key. You can take a secondary index and you can do some limited querying with secondary indexes, or you could go across your partitions and you could say, find all of the people who, I don't know, live in California and are registered to drive a car, right? If I've got a database, a DMV registration or something like that. So I could find all the cars in California, for example, in Cassandra. And that's pretty easy. Those are pretty straightforward queries. But if I want to do a more advanced query, and I want to say, well, look inside of this particular field, which Who knows? Maybe it's an XML blob, right? Maybe somebody decided to store some JSON in there. I'm not saying these are things you should do. But I want to look in there and I want to find, I don't know, maybe I'm looking for, let's see. Let me think of an example here. Maybe I'm looking for all the instances in which someone talked about. All right, let's say I'm NSA. I want to find all the instances where somebody mentioned pressure cooker and bomb, right, in the same document, right? So I want to actually look inside the field and find a near query. Find two words that are close to each other, right? Solr is actually pretty good at that. Lucene itself is actually pretty good at that. So basically, one of the things that we did with DSE is we said, hey, what if we took all of these partitions? And then inside the partition, we index the data inside the partition, right? And after we index the data inside the partition, we save the indexes on each local node. And then when we do a query, we could basically go in and we could say, send a Lucene query into Cassandra, distribute that query across the partitions, filter out duplicate partitions, and then return a result to a single coordinator and aggregate the result and give that back to the user. That's not unlike what Google does when it goes out and it crawls the web and indexes all the data. So distributed search is actually a pretty well understood problem and something you'll find in a couple of products out there. And something you could probably manage to do yourself in a small way. So distributed search is well understood, but it's still sort of being refined in the public domain. There are a couple companies out there working on it, Elasticsearch being one. Then on the Solr side, there's of course the Solr Cloud. But this is a well understood problem and interesting. And certainly something you can do inside of a distributed database, right? You may not get joins, you may not get your rich querying capability, but you can do the sort of filtering that you see done in many other platforms and on the web and things like that, right? So this is something that you can do. I don't know why this keeps taking me back there. Indexing, however, is not free, right? So when I go through all of my data and I want to index it, that means I have to read all of my data. That means if you move your partitions around or you split your partitions in your distributed database, that means you have to re-index your data as well, right? So indexing is certainly not free. And in a lock-free, high-velocity environment where you're writing data into your system as fast as it will take it, you can't just turn on indexing and expect things to keep up, right? Because now when I do an index or when I index my data, not only can I write my data, but I also may have updates that come in. And when an update comes in, I have to read the document and I have to re-index the document. Why do I have to do that? Because I may have a partial document or a partial row already written into the system. And I don't know, in most AP systems and in a lot of distributed systems, I don't require writes to be the entire document every time. I can update a field in a document. I can update a piece of a document. So now instead of my writes being, my writes not requiring a read, which is one big advantage that Cassandra might give to you, or many other distributed databases or any log structured store might give to you. Now instead of my writes being free of seeks, now I have to seek when I write the data into the system, right? And there's some things you can do to try to amortize this and say my indexes won't be immediately consistent, they'll be eventually consistent. There's some things you can do to do that and make it batch oriented, but indexing is expensive in distributed systems, just like it's expensive in SQL-based systems. So when you use these features, just be aware that you may be giving up some of the advantages that you got by having by choosing a NoSQL store or by choosing a log structured storage system, for example. Also, locking is bad, right? A lot of times people look at this and they'll say, well, when you write, just don't allow anybody to read that key until you're done indexing, right? And then write it back into the system. And that may be OK sometimes, but in a high velocity system, that's usually a recipe for disaster. All right. From an OLTP perspective, so that's sort of the OLTP side, and we're going to talk mostly about OLAP now. But from an OLTP side, you get something, which is you can distribute your data, you can scale to high velocities and high volumes, but you don't get the ad hoc querying capability that you had before, right? At least not at low latency. But you do get something that's scaled and guaranteed to scale and horizontally scalable, which we can't say necessarily about most relational systems that are out there. So the OLTP, on the OLTP side, you're relatively limited. And again, queries across partitions are slow. And you can mitigate that to a point by buying more hardware or buying more expensive hardware, right? I worked in a place a couple of years ago where this is right before I got into big data and working with Cassandra. So we were basically sticking all of our data on a single system, right? And when we had scalability issues, we bought a bigger box, right? Normal thing to do. We were scaling vertically. And at some point, when we bought a bigger box, we had to buy a bigger box with specialized hardware. And that was millions of dollars of an investment. And then we had to buy two, of course, because we had to have failover. And so we deployed the system. Things were working fine until the first system. On the primary system, some of the customized hardware, it didn't work out so well. It corrupted our data, and then it replicated the corrupted data to the slave. And when it replicated the corrupted data to the slave, all of a sudden we had to back up from tape, right? So we were doing this for an airline. And when you screw up an airline's system that allows people to board planes, that's a bad thing, right? And so they actually had to like email spreadsheets out and book people on the airplanes through the spreadsheets in some cases. In other cases, they just had to send people home because they couldn't do it, right? So we got sued. I didn't get my bonus, and I decided that I would put my money where my mouth was and say and not just tell my boss, hey, we should break up the system and store it in multiple places, but actually work on this somewhere else, right? So yes, you can scale vertically to a point, right? But at some point, it sort of breaks down, and it doesn't really work anymore. You have to put it on multiple machines. And scaling horizontally is actually great for analytics because the more machines you have, the more disks you can stick in your system. And the more disks you can stick in the system, the more IOPS you'll have. And the more IOPS you have, the more work you can do per unit of time for large amounts of data, right? Because we're talking about crunching data that doesn't really fit or doesn't always fit in memory anymore. So in this case, the questions that you're asking are complex. In this case, we're actually expecting that you'll be doing joins, that your algorithms are going to be iterative or parallel, and you're working on data in sets, right? The data could be structured or unstructured. We don't really care. But one of the things we still want to do is we still want to avoid ETL and query the data where it is, right? I don't want to have to take my data from a week ago and run analytics on it because I haven't had time or resources to ETL my data, or my ETL process failed, so I don't know what's going on, right? I don't know why this is happening. All right, so your options, right? The options that we looked at on the DSE side, and sort of the first thing that we did, we released something that we called Brisk. And what was Brisk? It was sort of an open source distribution of Cassandra integrated with Hadoop, right? The good thing was you could take this and you could run Hadoop jobs on your data in Cassandra without having to do anything else, right? You could just open up the Hive shell, you could write a SQL-like query, and run your queries on Cassandra. And that was great and easy to use. It allowed people to basically just run Hadoop, right? On the upside, it was easy. On the downside, we were now in the business of distributing Hadoop, right? If anyone here has ever tried to distribute Hadoop, or if you've even tried to figure out which version of Hadoop you should be using, from looking at like the Apache distribution and the Yahoo distribution and Cloudera distribution and CDH, and Ambari now, and in the Apache distribution, and Hortonworks. It's a mess trying to figure out which version of Hadoop you want. And then once you choose one of those distributions, trying to keep up with the project and all the patches that people are sticking in their particular distributions is kind of crazy and difficult, right? So instead of that, our second iteration, or something that we're doing now, is we're saying having this close relationship between our analytics platform and our OLTP platform isn't necessarily a great idea for multiple reasons that I'll talk about. But one of the things that is important is that you allow people to use Hadoop with your platform, right? Or if people want to use Hadoop, make it easy, right? And so we've got input and output formats, SerDes, for that will interoperate with Pig and Hive. And you can write a job against Cassandra relatively easily, easily using Java. And then there are a bunch of other things, Spark, Shark, Presto, right, are some of those options. And again, you guys are going to know me really well at the end of this, right? So we shipped our own at first, again, and we called it Brisk. But upgrading and maintaining that is difficult, right? To the point that it's almost not worth doing because people will tend to roll their own because they want the latest tools, they want the latest features, the latest stuff that's being shipped by the Hadoop project, right? This is something you probably want to avoid if you ever end up in the situation where you want to add analytics into a platform that you're building. It's much easier, again, to ship integration. All right, so the problem with Hadoop, though, even if you get it running and working, is it's relatively slow. So traditional Hadoop is slow. When you run a Hadoop job, like when I would do training and I would say, okay, here's our Hadoop integration, and now you can write SQL queries on Cassandra, and people get really excited. They were like, ooh, I can run SQL queries on Cassandra. That'll be awesome. I can do a join. I can do a group by. I can do all this cool stuff, right? And then they sat down at the Hive shell. They wrote their query. And at the end of it, they'd just be like, that took me like 2.5 minutes to do a group by on 10 records, right? I mean, it's ridiculously slow for some stuff, right? And sure, there's the overhead of starting the job, and sure, there's overhead of job trackers and task trackers and all of that stuff. But still, it's slower than you want it to be for a lot of things, right? And it's also it's complicated to set up. It's hard to use in many cases, and it mostly uses Java. And I've been writing mostly Java code for the last 5 years. And it's a good language, right? But there's some other things in the world that are better. And there are better fits for what we're trying to do, right? Java is good for some stuff, but it's not a great language for querying data, right? So there's other stuff that's out there now that's worth looking at. Spark is a generic computing platform that also interoperates with Hadoop. And it's got plugins and interoperation today with Cassandra. And at DataStax, we're working to make that better. And we've got a partnership with Databricks that we just announced where we're going to try to make Cassandra one of the best platforms to use along with Spark. Has anyone here ever looked at Spark before? So Spark is based on Scala, and it's basically, again, generic data processing. It's based on the ideas of these resilient distributed data sets. That's what RDD stands for. And Cassandra is a really cool platform to work with this style of analytics because you've got in a Cassandra cluster, you might have 100 nodes, right? And on each one of those nodes, you probably have anywhere from 300 gigs to a terabyte of data. And when you've got that much data, or you've got data in that range, you can fit quite a bit of that data in your working set. And what one of these resilient distributed data sets does is it says, all right, I want to work with this piece of data. So it'll take that data and it'll actually stick it in a cache in memory and try to keep it in memory as much as it can. And then when you run your analytical job on it, it'll do the processing in memory rather than having to go through all of the data in disk, or as much as possible in memory. And so a lot of times where a query in Hadoop might have taken you 10 minutes, this might take you a couple seconds, right? A lot of the queries, I've got some smaller data sets that I work with, and for a demo that I have, and I can relatively easily and relatively quickly query that data, and a lot of my queries come back within 81 milliseconds. Some very fast data processing you can do with Spark. So Spark is one of those emerging technologies you should keep your eye on if you're interested in data and data processing. every single one of the Hadoop distributions has picked it up and put it in some shape or form into their product, mostly, in my opinion, to stay relevant, because Spark is certainly taking the analytics world by storm. And I'll try not to do that. Try not to use a pun. Remember I said Java is hard? Well, this is probably the simplest MapReduce, or the simplest program you'll ever write that will do MapReduce, right? There's a lot of boilerplate, or some boilerplate code in here. I didn't include the boilerplate, but there's some boilerplate code in here that's not included. But it's not super straightforward what's going on here. You kind of have to spend some time with the code to figure out what's going on. And it's quite a bit of code that you have to write compared to what you have to do in Scala. Sure, it's Scala and it's something else you have to learn, but this is a language, a functional language is more aptly suited to a functional problem, right? And data processing or set processing in many cases is a functional problem. So this is how you would write a similar MapReduce program in Scala using Spark. Now, if you like SQL and you want to write your queries in SQL, there's another thing that in some ways is like Spark that was also released by the Facebook project called Presto. And Presto allows you to do distributed queries using SQL. It follows the same theme that I've been talking about, is that data should be processed where it is. We shouldn't have to ETL our data, or if we've got an operational data store, we should be able to query it there rather than having to ETL it somewhere else to do our processing or our data processing. And there are a bunch of connectors for Cassandra, HDFS, and a whole bunch of other stuff, right? And then there are other things, right? Other types of analytics and other types of querying data. Some of the things that we've been looking at lately are GraphX. GraphX is a plugin for Spark that allows for analytical graph processing. And then there's Titan as well. And Titan, and I got these backwards, Titan is more the OLTP side. GraphX is more the OLAP side. But Titan allows you to create graphs create a graph data structure on top of Cassandra and then query those graphs out, right? So there's a lot of stuff, right? A lot of stuff on when you're building your own data platform. If you have to start sharding your data, you're basically building your own data platform at that time. And your users will come to you and say, I like that you're giving me all these OLTP capabilities that I had before, but I need you to run a report, right? And so these are things that you want to keep in mind as you build that platform, and you make sure that those capabilities will continue to be available to your users, because it's guaranteed that if you're building a system at scale, then you'll need to solve some of these problems yourself, or you'll need to choose a platform that will allow you to solve them relatively easily. So again, I work for DataStax. We're hiring. If you want to work in an awesome environment, it's a great place to work for sure. And you get to work on hard problems and difficult problems. So any questions? No? All right. Thanks.